computer model from a very powerful American computer program which uses real-time data for weather and the wind directions and all these meteorological data. And it shows the releases from the Fukushima plant on the 21st of March. I'll just play through it again when it finishes. It was quite difficult to get this to run, so here we go. Now, you can see to the south is Tokyo. So it's now going over Tokyo, and it's moving across the whole of Japan. Now, if you look at the agenda, you will see that I'm from the University of Liverpool, and I'm going to talk about radium and thorotrust. But actually, I'm not from the University of Liverpool, and I'm not going to talk about radium and thorotrust. Maybe a little bit. What I'm going to talk about is Fukushima, and I'm from the University of Ulster in Northern Ireland, and also various other places, which I won't bore you with. And we shall talk about Fukushima. And if there's any moment at the end I can say something about radium and thorotrust. Oh dear, what's happening here? I don't like this. I think there may be some problem here with this. There we are, that's the one. Good. Okay, can you deal with that? Okay. So I'm going to talk about the cancer yield of the Fukushima catastrophe, which I've done some work on recently. And there's not a lot of time, so I'll take you through this quite quickly. But you can ask questions, and I have two other things to talk about. Now, what we have done is we've applied the risk model of the European Committee on Radiation Risk to the health effects of the Fukushima catastrophe on the basis of what we know at the time when I wrote this, which was last week. In order to work out how many people are going to get cancer, we have to know the doses from the radionuclides, and we have to know the population. And we don't know the doses from the radionuclides exactly, but so we can't exactly calculate it on the basis of the ECRR model. But there are some things that we can do. We can make some assumptions. And there are two ways in which we can approximate the internal dose, which give about the same result. I can calculate the area contamination on the basis of the gamma radiation dose rate. That's the first thing I can do. But I can also look at the reports of the IAEA on the contamination levels, because these have been reported. And then I can use one of those pieces of data to convert to the other. I'll show you how we do this. This is a graph taken from a British government publication in 1971, when everybody was expecting nuclear war. So they wanted to know what the dose rate would be when you knew what the contamination was for different types of isotopes. This is a very, very important graph, and it's out of print now. But all of this is on the internet if anybody wants to download this graph. It's a very, very useful graph. So if you know the contamination, you can work out the dose. If you know the dose, you can work out the contamination. So if you know the microsieverts, you can make it megabecquerels per square meter. Well, from using cesium-137, this is what you find. You find that if you have a dose rate of 1 microsievert per hour, then the contamination is 300 kilobecquerels per square meter, or 0.3 kilobecquerels per square meter, and you can just multiply. So if it's 5 microsieverts per hour, you can find that it's 1.5 megabecquerels. Incidentally, as you maybe know, 1.5 megabecquerels is higher than the Chernobyl exclusion zone. So the first way that I do this calculation is I use the results of the study of Tondell in Sweden in 2004, who found that there was an 11% increase in cancer for 100 kilobecquerels per square meter. So if we can work out the number of kilobecquerels per square meter in Fukushima, we can say how many percentage there is increase in cancer. I recommend a study by Tondell, which is a very good, powerful epidemiological study. So first we need to get the exposure. Well, there are various places that we can get the exposure. People telephone me from Japan with levels on their Geiger counters. But the official data is from the Japanese ministry, and this is the website where you find this data. And this is a map which I made from the data which there was, and you can see I've written here in red the microsieverts per hour that they're measuring on the ground. This is what they measure with a Geiger counter. So these are real measurements. This is 20 kilometers, this is 30 kilometers, this is 50 kilometers. So we know what the doses are according to the MEX website in microsieverts per hour. And of course you remember that we can turn that into contamination, megabecquerels per square meter. Because if we have 5 microsieverts per hour, say we have 10 microsieverts per hour, that's 3 megabecquerels per square meter. 10 microsieverts per hour, 3 megabecquerels per square meter. So if we go back here, we find that there's many places where there is 10 megabecquerels per hour. There's one there, 5, 9 here, there's 18, 20, right out there. So we've got the dose rate and we can calculate the exposure. And of course from Tondell, where are we? Here we are, yes. And so from Tondell we know that there's an 11% increase for every 100 kilobecquerels. So we have everything we need there. And we can work out the contamination, and this is what I worked out. This is the approximate contamination to these different distances. So you can see here that from 0 to 20 kilometers, the contamination is about 4 megabecquerels per square meter. There. And in fact, it's pretty even. So even out to 50 kilometers, it's about 4 megabecquerels per square meter. So it was a very serious accident. If you go out to 50 kilometers, you have an area which is 7 times larger than the Chernobyl exclusion zone. And the contamination is about twice to 3 times. So we already know that the contamination is much greater than the contamination from Chernobyl out to this distance. I'm not talking about a long way away now. So we can now go to the IAEA bulletins and ask the same question. In fact, the IAEA bulletins are lying. We can say that for sure, because we've already done this calculation, and they have said the surface contamination here is between 0.2 and 0.9 megabecquerels per square meter. So it's actually higher than that. But never mind, we can just say that that's what it is and go on from there and see what happens. And of course in the prefectures very far away from the accident, Ibaraki, which is 100 kilometers away, and Tokyo, which is maybe 200 kilometers away, and some of these prefectures are very, very far away, we are still getting an increase in the radiation, which gives you an increase in the concentration on the ground of contamination. And these graphs are available on the internet. These are the official exposure rates. And this is the exposure rate at Ibaraki, which is 200 kilometers from the site. And you can see here, at this point here, it suddenly went up. And this incidentally was not an event that was even reported. This is after the explosions occurred. The only thing that happened when this went up was that smoke was coming out of one of the reactors. Smoke, white smoke it was, and everybody ran away. But that's the only thing that happened. There was no explosion, there were no bangs, nothing reported. But there was a sudden increase in radiation at Ibaraki about 3 or 4 hours after this event. And you can see that this radiation stays up high, so it goes along, it's already a little bit high. The background rate should be about 0.05 here, so it's down there somewhere. So it's already a little bit high, and that goes up even higher, and it stays high, which means that that stuff stays on the ground. And that level is still high. So to work out how many people are going to get cancer, we need to know the population. So this map is a population map from the Japanese census data on the internet. And what I did was I drew some circles, 50 kilometers, 100 kilometers and 200 kilometers, those circles are. 100 kilometers, 200 kilometers. This is Ibaraki here, this prefecture here, that's the one we were just looking at. And that's Tokyo there. And then what I did was I cut them out with scissors, and I weighed them on a chemical balance to work out the areas. This is a spectroscopic trick that I used to be a spectroscopist, so it's a very easy way of getting areas. And this is the answer. So in the 100 kilometers from Fukushima, there are about 3.3 million people. And in the 100 to 200 kilometer area, this is just this bit here. It's very highly populated, this bit, that bit. In that area, there's about almost 8 million people. So a lot of people are going to get exposed to this radiation. So let's go to Tondel. So on the basis of the measurements and arguments that I've just put forward, we can assume that the 100 kilometer radius is contaminated uniformly to 600 kilobecquerels per square meter. Incidentally, that's extremely conservative. It's probably at least twice, maybe 3 times that, but let's go and see what happens. So the dose associated with this level of contamination is this should be microsieverts. I'm sorry, that's a typo. 2 microsieverts per hour. This is wrong. Okay, that should be 2 microsieverts per hour. If it was 2 millisieverts per hour, everybody would be dead. Now, assuming nobody moves away and that the contamination remains at this level, and we use the Tondel regression coefficient, we can calculate the increase in cancer. Now, the cancer rate for all malignancies, for all cancers in the Japanese population, is 462 per 100,000. And so, therefore, the annual number of cancers in that population is 15,000. And in 10 years, there will be 156,000. But of course, if it increases by 66%, which is the Tondel risk coefficient, there will be 103,000 extra cancers due to the Fukushima explosion. This is quite a large cancer yield if those people stay there. If they don't stay there, then it will be less, of course. But so far, they're being told, on the basis of the ICRP risk model, that it is safe because the doses are going to be lower than natural background, or they're going to be around natural background, or whatever. The usual argument is being put forward that this is safe. These levels of radiation are safe. But they were not safe for the people in northern Sweden at much lower doses. Now there's another way we can do this. We can use the ICRP model. We can calculate the same dose. We've just done this. And the annual dose is 17 millisieverts if you have 2 microsieverts per hour. And so the ICRP model predicts 2,800 cancers. So you see the difference is it's either 100,000 cancers from the Tondel method or 2,800 cancers from ICRP. And that's in 50 years, incidentally, whereas Tondel is just for 10 years. So there's obviously going to be more than Tondel because people aren't just going to die of cancer in 10 years. They're going to continue to die of cancer there, and also in Sweden. Okay. And so you won't be able to detect that using normal epidemiology, that number of cancers you can't detect. And we've heard all of these arguments after Chernobyl, that the predicted number of cancers after Chernobyl is too low, you can't detect them. So if somebody comes and says, hey, look, everyone's got cancer, they'll say, well, it's not from the radiation. It must be from the radiophobia or drinking too much vodka. So now we can use the other method. We can go to the ECRR 2003 dose method, and we can assume that 1/3 of the dose is internal, and 1/3 of the internal dose carries the weightings of 300, which is the approximate weighting factor which we obtained from many, many studies, and which also fits Tondel, incidentally. So we can predict the number of cancers that Tondel found in northern Sweden from this method. And what we find then, if you go through all of the sums, is that the lifetime 50-year cancer yield is about 200,000 extra cancers using the ECR method. But that's 50 years. So Tondel is 100,000 in 10 years, and the ECRI is 200,000 in 50 years. So they're pretty similar, and this is the predictions here. In that population out to 100 kilometers, these are the predictions. The ICRP predicts 2,800 in 50 years, Tondel predicts 103,000 in 10 years, and the ECRI predicts about 200,000 in 50 years. So Tondel and the ECRI method are roughly the same, and very much more than ICRP. So this is a prediction. I predict to the world that this is going to happen if these people stay there. So this is a prediction before the event. We can also look at the same calculation on the basis of the people living in the 200 kilometer area, and we found, again, it's a similar number. There's 120,000 extra cancers in 10 years, or 224,000 cancers. So of course, what we're saying is that in total, there's going to be 400,000 cancers in that area. And this is not including, and then we can do calculations for Tokyo and for other areas and so on. There is a problem. For the high exposures, it's almost certain that the risk will not be linear. It will not be a straight line. And this is assuming that all these calculations assume a linear response, so that you double the dose, you double the cancer. But the problem is that if you get high doses of radiation, then as we've just seen with the liquidators, you die of something else. The cancer rate goes up with age, very sharply, exponentially. And so if you die at the age of 45, or 40, or 50, from heart attacks or other problems, then you don't die of cancer. So there is a turning over of the cancer risk. So, and also these predictions are based on the idea that the population will stay there, so they will remain in the 100-kilometer zone. And of course, if they're taken out after 1 month, then probably it'll be about 1/12 or maybe 1/6 of that. So the reason, there is a very strong reason for evacuating people now, as soon as possible. And I heard this morning that another nuclear reactor is giving trouble in Miyagi prefecture. So there seem to be some big problems. And so this is working now, miraculous, look at that. And so this is the reason, you see the reason here, why these high levels of radioactivity are being measured. And incidentally, we never see this model on the television. So whenever they show models of the radioactivity coming from the nuclear plant, you will always see it blows out to sea. It always blows out into the Pacific Ocean. It never does this. So that's my take on Fukushima. And I have, how much time have I got? Because I don't want to talk about radium, really, but I do have one other thing that I wanted to do. So what have I got? Okay, so you want to finish here? Or give me 5 minutes more for this segment, okay? I won't bother with the am I over time? I didn't think so. Anyway, let's get rid of this. How do I do that? There we are, okay. So this is what I want to show you now. I want somebody who speaks German to help me. I also want us to open up the phone. This is a word file, this one. Find it on the floor. Alright, now I need somebody to read this in German. Okay, you want to do this? Sebastian, can you read it? Read it from the screen or read it from here?
Kann ich versuche das vorzulesen. Das ist ein Brief an Lenze. Die Ereignisse in Fukushima was mit hier was Die Ereignisse in Fukushima, Japan, bringen unsere Aufmerksamkeit auf die Gesundheit der Bevölkerung, die durch die radioaktive Bestrahlung aus den havarierten Reaktoren und Abklingbecken bestrahlt worden waren. Die Anweisungen der internationalen Behörden über das Risiko der Bestrahlung im Zusammenhang mit der Strahlenbelastung in den genannten Gebieten wird von der Bevölkerung in den belasteten Gebieten ernst genommen und umgesetzt. Was diese Leute entscheiden, ob sie zu Hause bleiben, was sie essen und trinken sollen oder ob sie fliehen sollen, ist entscheidend für die Zukunft ihrer Kinder. Diese offiziellen Ratschläge und Angaben der internationalen Behörden beziehen sich auf die heute akzeptierten Risikomodelle. Diese Modelle werden von der ICRP mitgetragen und beruhen auf Angaben der ANSCER. Es ist ein wissenschaftlicher Imperativ der Wissenschaftsphilosophie, dass für alle Erklärungen ein Vergleich zwischen ähnlichen Ereignissen gemacht werden sollte. Das ist eine alte Weisheit von Mill 1887. Der beste und adäquate wissenschaftliche Vergleich, um die Konsequenzen für die Gesundheit in Bezug auf die radioaktive Bestrahlung in der Umgebung von Fukushima einschätzen zu können, ist, die radioaktive Belastung durch den Unfall in Tschernobyl heranzuziehen. Die Modelle der ICRP und der ANSCER beruhen aber auf äußerlichen Gamma- und Neutronenbestrahlung. Sie beziehen sich auf die Beurteilung der Bestrahlung der japanischen Bevölkerung, die 1945 Opfer der Atombomben wurden. Wenn wir die neueste Publikation der ICRP von 2008 betrachten, sehen wir, dass viele hundert wissenschaftliche Studien, welche die Gesundheitseffekte der bestrahlten Population durch das Tschernobyl-Unglück behandeln und die klar und deutlich beweisen, dass das ICRP-Modell mindestens 100-fach falsch ist, gar nicht zur Kenntnis genommen werden. Dies beunruhigt uns zutiefst. Schlimmer noch ist, dass der ANSCER-Bericht von 2008 über die Auswirkungen auf die Gesundheit diese oben erwähnten Studien mit keinem Wort erwähnt oder diskutiert. Als Belege und um zu zeigen, dass das von der ICRP dargestellte Modell falsch ist, können wir 20 Studien zitieren. Es alarmiert uns, dass ANSCER und ICRP sowie andere nationale und internationale Agenturen nur die Studien herauspicken, die ihre These unterstützt, und sie ignorieren die Studien, welche ihren Thesen zuwiderlaufen. Der Philosoph Popper sagte 1962, Wissenschaft kann sich nur durch Falsifizierung von bestehenden theoretischen Modellen und experimentellen Resultaten nach vorne bewegen. Sie kann sich nicht bewegen, wenn diese Theorien, welche die bestehenden Modelle falsifizieren sollten, aus der Diskussion ausgeschieden werden. Im Fall von Fukushima muss man sagen, dass durch die Nichtanerkennung der Resultate in Bezug auf Tschernobyl, von Tschernobyl zu vielen zusätzlichen Todesfällen führen wird, wenn die ICRP nicht aufgehalten wird. Unterzeichnet Basbi, Gabokov, Marco und so weiter.
Right. And the point about this is, like Mark said, philosophers have interpreted the world. The point is to change it. What I want everybody here, all of you clever researchers, to do is to put your names on this letter. So you can tell the authorities here, tell Sebastian or Thomas, if you want to sign this letter. And then this letter is in English. I put it in German. Cornelia kindly translated it. And this letter is in English, and it will go to the British Medical Journal and to the Lancet, who don't like me, but they're frightened of me. So with all of you clever people on there, with all of your, where you come from, and you're head of this, and director of that, and researcher of it, and all the research papers, I will make it so difficult for them not to publish it that they wish they hadn't been born. So that's it. Thank you very much. There was somebody wanted me to show some. There was somebody wanted me to put up another picture. You can have my stick. I'll whoever it was. Anybody wants this data, they can have it. Okay.
Can you put online?
You want it up now? Is there time? I think there's time. I don't think there's time, you know.
Will you put it online?
Yeah, they can. Yes, it is. It is already online. If you go to, I'll show you.
Was? Wahrscheinlich shared.
Or cesium. Cesium?
Radiology vielleicht. Effects.
And on B is RW.
You can take all this stuff, it's all online, all right? So you can find it. I mean, I don't want to hold up the proceedings anymore. Somebody else should come and talk.
Vielen Dank für die offene Diskussion.
Dear Chris Busby, I really appreciate for very interested report to you.